Hello again. So, in the previous part, we introduced some basic concepts of smart grid and the need or the benefits of using a smart grid, and also some introduction to telecommunication. And in this second part, we continue the telecommunication part. So, we said here that it is really challengeable how to make the communication successful between any two terminals over the same channel. And to do that, we need to have some protocols, and those protocols usually they follow certain layers. So to make it like easier to analyze, to make it more flexible in order to improve the communication and so on. So usually the communication could be divided into layers, and we have like 7 layers in the standards, but like in OSI standard, but here we show only the 4 layers. And in the 4 layers, we have the layer of the physical layer. It's called the physical communication, where we have the modulation, the antennas. It can be laser, or it can be electromagnetic wave, or it can be whatever. So this is the physical layer, where we have the physical part. And then we have the second layer is the data link layer, where we have the media access control, which is like responsible about making the communication between every two terminals inside the network successful. The physical addressing of the the data, because for sometimes that we have like a lot of receivers, but the data is going to only one terminal, so we have address here. So here the physical address is giving in the data link layer. We have the error detection and error correction in the data link layer. Also in the we have above the data link layer, we have the network layer, where we have the logical addressing, we have the packet paths and the routing, and so on. Then we have the data and application layer, where we have the information sync, or source encryption, decryption, compression, identification, and so on. And also the application is the source itself. For example, if you have a sensor data and so on. So those are generally the 4 layers of the major telecommunication layers. One thing interesting here, so you can, for example, adapt or change one layer without like major changes of the other layers. For example, in the smart meter, we said here, when we talk about the smart meter, you can see that here we have the physical communication here, the physical communication. So in the physical communication, what communication media that you use, okay, it shouldn't affect that much the structure or the data inside the smart grid, as far as it is enough for the requirement. What I mean, for example, if you have data that you need to send with certain data rate, or with certain throughput, then the communication media should be able to achieve this like minimum required throughput. Okay, but for example, if you change from 4G to 5G, you don't need, or you shouldn't be need to change the whole smart media structure. So the same concept here, that in the communication layer, so if you need to change one of the layers, it is not necessary to change everything. So this makes the communication system much more flexible. Okay, and usually the signal or the information that we need to send, like control signal, voice, image, video, sensor data, whatever, are transmitted in forms of electrical signal. Okay, so electrical signal, where is the information actually? What a change in the electrical signal which carry the information itself? So it is the shape, so the fluctuations of the signal with time, it carries the information. It is like when I talk now. If we have oscilloscope for the signal, for the voltage, for example, you can see that for every letter it has certain frequency, okay, and also certain time shape in order to have every letter. So in that, it is called for every font, for example. For that reason, that the data usually is represented by electrical signal, which have like fluctuations in time in order to have the information. Okay. We can see usually the signal in time, but the signal itself, the rate of changes of these fluctuations is known as frequency. So the signal, it has the time domain where the signal like naturally changes in the time domain, but also the rate of changes is called the frequency inside that signal. Okay, so the frequencies itself, the rate or the spectrum of the changes of the frequency is called the bandwidth. The signal bandwidth. The signal bandwidth is the change or the rate. For example, if we have a signal that the frequencies might change from 500 hertz to 1000 hertz. Okay, from 500 hertz to 1000 hertz, what is the band? The band is 500 hertz. So we can say here that the bandwidth of this signal is 500 hertz. So the bandwidth is the rate of changes of the frequencies from the minimum frequency to the maximum frequency in that signal. For a human voice, usually the signal changes from about 200 hertz or actually it can be even less, up to about 4 or 5 kilohertz. So this is for the human voice, the minimum requirement for the voice. It is about 4 kilohertz. Okay, to have like good quality voice. Of course, you can reduce it, but you will reduce the quality of the voice. However, the human ear, it can sense the frequencies from lower, like about 15 hertz or 20 hertz up to 18 or 20 kilohertz about. But most of people, the maximum is around 15 kilohertz. Okay, so this is the bandwidth of the information. Generally speaking, in the baseband, as more frequency or more spectrum you have, is more information you can send. This is generally. I mean, it might be there's some like special cases, but generally, as more in the baseband, more or higher bandwidth means that more information that you can send. Okay, so for this reason, for example, the voice signal bandwidth, it can be like compressed up to 3 kilohertz only, but for video signal you need much more. To have like good quality video signal, you need of course we can use a lot of compression techniques, but in the baseband you will need much more bandwidth than needed by the voice signal. Okay, how the signal could be transmitted? Of course, we cannot send the signal in its baseband. For example, now if I have a microphone to change my voice into electrical signal, it is useless by itself. Yeah, I mean, I cannot connect to the antenna or to the internet or anywhere. Okay, so what we need here, we need to modulate the signal, to make it like, to prepare it for the purpose to be transmitted, and also for the channel. So how to modulate the signal? The baseband signal usually could be modulated by the parameters of the sinusoidal signal, because the stem of waves is the sinusoidal wave. So the sinusoidal wave is the only wave which has zero bandwidth. It has zero bandwidth, and I will explain what I mean by zero bandwidth. Of course, this is ideally the ideal sinusoidal wave. Okay, and okay, let us go to the next slide. So you can see this is the sine wave. This is typical sine wave, that x of t, that it is real sine wave. The complex sinusoidal signal is the exponent of j, like 2 pi 0 t plus phi. But here, the one of the real types, it can be cosine or sine, of course. The difference is only 90 degrees. So we have the amplitude of the cosine wave, we have the frequency of the cosine wave, and then we have the phase of the cosine wave. Okay, so this is the amplitude or the change, the fluctuations of the sinusoidal signal in time domain. Okay, in the frequency domain, now if you look to this signal in frequency domain, you will find like delta like impulse at the frequency f0. But this delta, the width of this delta is 0. It doesn't have any width. It is only 0. I am talking ideal, for the ideal sinusoidal signal. So the width is 0, which means that it has 0 bandwidth. It has 0 bandwidth. So it is the stem of all waves. Is the sinusoidal signal. Okay, there is no time to explain why here, but the cosine wave is also the signal which is used to modulate all information before transmission over like different communication media. Okay, so the communication or the modulation, what is the meaning of the modulation? The modulation where we augment our information, where we put our information. The information could be in the amplitude. Then we have amplitude modulation. It can be augmented in the frequency. Then we have a frequency modulation, or FM, or it can be augmented in phase. Then we have phase modulation. For digital communication, the most efficient one is the phase modulation, and then we have also a quadrature amplitude modulation, where we have phase and amplitude, and this is known in digital communication systems. Okay, so the basic blocks of digital communication system, we have the analog signal, for example, from sensor, okay, or we have maybe we have already sensor that or device that generates directly digital signal, so we don't need to go through the analog to digital converter. Then we have the source coding. The source coding is very important, for example, for compression, for example, and also for equalization of the signal and so on. Then we have the channel coding. Channel coding is also very important for error detection and correction and increasing the reliability of the communication. Then we have the digital modulation, where we prepare the signal for transmission over the channel. So here we make the digital modulation with, for example, phase modulation or amplitude modulation. It is called amplitude shift keying or phase shift keying or QAM, or digital amplitude modulation, and so on. Then the signal goes through the channel. Then the receiver, we have just the undo operation. So we have digital modulation here. In the receiver, we will have digital demodulation. Here we have channel coding. Here we have channel decoding. Here we have source coding. Here we have source decoding, until we have the original signal again. It will be like retrieved at the receiver part. So this is very general, the digital communication blocks, the major digital communication blocks. Of course, there are many other blocks that they are omitted from here, like for example the multiple access block and multiplexing and so on. Okay, now we talk about media access control. How can we achieve many communication transmission over the same channel? This is a very important question. Okay, to explain this, let us have an example that we are in like a classroom now. So all of us, we are in classroom, the teacher and also the students. We are in the same classroom, okay? And let us, in that classroom, we have like 50 students and the teacher, okay? Yeah, so when the teacher is talking, then it is like a broadcasting. So the teacher is talking, the others are listening. So it is a broadcasting protocol, okay? So it is one direction. Of course, in this case or this example, we may have also the reverse direction. So assume that we have like broadcasting, but the last student in the room, that he was not able to hear the teachers, then he asked the teacher to raise his voice. So now we have like control channel in this communication to ask the transmitter to increase the power in order to achieve the quality of service inside the classroom. So but this is still broadcasting, because it is the information flow is from one source to the receivers. Okay, now let us say that we want the students to talk to each other. Okay, sorry, that each two students wants to talk to each other inside the same room, inside the same physical area. Okay, what will happen? Not necessarily that the students are sitting at just each other. So for example, randomly the students want to talk, and maybe they are in different locations inside the room. For those who are closer to each other, they might control, they might talk to each other successfully without any, like, of course they will hear some noise, but still they can talk to each other. Okay, but if we have two students far away from each other and they start to talk, and then we will have noise, because we will have a lot of noise, then they will start to raise her voice. The transmitter will start to raise the voice in order to reach to the voice to reach to the destination. Okay, and when they raise the voice, then the interference will increase also to the other transmitters, the other students. So the other students will also, everyone will start to raise his voice in order to reach the message to his like destination. And what happened after that? After a while, this classroom will be just a mess. So a lot of noise, and maybe the communication will fail between most of the pairs inside that classroom. As I said, maybe those who are just close to each other, maybe the only ones that they will have successful communication, but the others will have like failed communication system. So in that sense, how can we make media access control in that sense? Okay, now we have two options. The first option, that we have controller or organizer for this room. Let us assume that the teacher is the organizer for this room. Okay, so in that case, the teacher can divide the time between the students. So they will say that, okay, now we have this time for pair 1. So now you send your message to your destination, done. Okay, now we give the time to the second pair, then we give the time to the third pair. Okay, so this can be like in this way. So it is like time multiplexing. So we have time multiplexing between students. Now we will have successful communication. Yeah, but also the organizer can be like smart enough that if we see two students close to each other, then we give them the opportunity to talk. Okay, and we don't include them in this process, because they can talk without making a lot of noise to the others as well. Okay, so this is called time multiplexing between users. Okay, is there other possibility? Yes. For example, if students have different like background languages, okay, then they might, every two students, they might be able to talk in different language. For example, two students, they communicate in English, two students, they communicate, for example, in Chinese, two students, they communicate in Arabic, so two students, they communicate in, for example, Italian, and so on. So what happened? The human brain has the ability that when there is noise and and it is not understandable, then it is easier to be removed. Okay, or to be dimensioned. Okay, and in that case, we might have like different communication, successful communication, even they are both or all of them, they are talking in the same time and in the same frequency, but with using different languages. So this is also in communication, we call them like code division multiple access. So we give different like and orthogonal codes, or of course it not necessarily be orthogonal 100%, but different codes with low orthogonality. between different codes to each terminal. Then we have, this is called CDMA, and this kind of media access control, or the multiple access, it was used in the third generation and in different communication systems, as we will see later. Okay. The third option, which is maybe difficult to explain it now in this example of a classroom, but is the using the frequency, dividing the available spectrum between users. So each two users, we give them different frequency band, so they don't interfere with each other. So this is called like contention-free multiple access. There is no like competition between students when we have organizer. When we have organizer, then we can divide the time between students, we can divide the frequency, we can divide also the orthogonality, or the different signal to be orthogonal, and actually we can also divide the space. So in wireless communication, it is possible to use like multiple antennas where it will have like main loop of the antennas in toward the direction of the destination. So each two students, if we assume that they use some kind of like horn, some kind of horn, when they talk, no one will listen except in the direction of that horn, for example. In that case, we can also divide the space between students or between terminals. So basically, we have like four those in communication, that we call them like radio resources. We can divide the time, we can divide frequency, we can divide space, we can use the orthogonality principle between signals in order to have contention-free multiple access. But remember, this needed, this needs a network with a backbone, with organizer, like a cellular network. So in the cellular network, in mobile network, we have the base station. So the base station working as the organizer between users. And here you can see how to divide the resources. For example, in frequency division multiple access, every color represents different user, so they can use the whole time, but we divide the frequency among all users. In the TDMA, all users, they can use the whole frequency, which means that they can send more information, but we divide the time between them, and naturally there are some signals which are already discrete in time. Then we can utilize this feature in order to have this time division multiple access. Or all users, they can use the all time and all frequency, but with different and orthogonal codes. But because we cannot have like 100% orthogonal codes, even if we have them in the transmitter, they will not be orthogonal at the receiver, because due to the multiple paths and because of the channel. So in that sense, we need to be careful about the power. The power should be used carefully in order to like avoid the destructive fading, or destructive interference between terminals. Okay, here we have some figure about how to use in the frequency shift and the frequency division multiple access, and also the time division multiple access. You can see here that we need synchronization here in order to divide the time between terminal A and terminal B, where that each signal will reach to A and B. Okay, and this is for the code division multiple access. You can see that for the codes which have small like orthogonality, it means that we have sigma ij between code I and j. It can be 1 if I is the same as j, but it is much less than 1 if I does not equal to j. Okay, so what kind of networks? As I said, we have the cellular network, and we have right now we have like 5 generations. The first generation is for the cellular network, mainly using frequency division multiple access, and it was analog. The second generation, one kind is JSM, that maybe many of us remember it. So it is digital communication system, and it uses time division multiple access with frequency division multiple access. In the third generation, we use the UMTS. It is still in use, where the system using mainly the wideband CDMA, code division multiple access. And the fourth generation, like LTE, they use the orthogonal frequency, the division multiplexing of DM and of DMA. Okay, and the fifth generation, actually it is very similar to the of DM, but not necessary to use orthogonal frequency division multiplexing, but they use non-orthogonal, actually non-orthogonal multiple access. We relax the orthogonality concept in order to increase the number of users in the network, but using, of course, much more sophisticated like algorithms in order to remove the interference according to the non-orthogonality between bands. Okay, so this is for the network structure with the backbone. Now we have the contention-based multiple access, where what happens if we don't have organizer? How can we arrange and manage successfully the communication between pairs? This is what we are going to talk about in the next part. Okay, thank you.